Everybody, it's Eugene Leisher here, and welcome to Forensics Talks. This is episode 28, and before we get started, just a few little announcements here. So I'm going to share my screen so that you guys can see a couple of things here. So the first thing that I want to talk to you about is the photogrammetry week. So today is actually the third of 3 webinars. It's a trilogy, and if you're interested in learning photogrammetry, then you can just go to my website and sign up there. So as soon as you get there, you'll see that there's a registration thing. There's still time to register, even though this is the very last one. Also, the Canadian Society of Forensic Science is going to be hosting a conference, a virtual conference, the week of June 21st and 24th. I'm actually one of the organizers for the conference, and I'm happy to say that we've got some really excellent speakers. We got workshops, some networking events, and that sort of thing. So unfortunately, because of COVID, a lot of the Canadian forensic science conferences and identification conferences have been canceled. So this is probably going to be one of the only ones for this particular year. And there's going to be a broad range of topics and subjects that are going to be covered. So yeah, if you're interested, make sure that you attend there as well. Alrighty. So for today, I want to introduce Dr. Geoffrey Morrison, and he's a Canadian forensic scientist who specializes in forensic inference and statistics and in forensic speech science. And he originally studied science and engineering at the University of Dundee, but eventually got his PhD from the University of Alberta through the Department of Linguistics in 2006. He's the director of the Forensic Data Science Laboratory in Aston University in Birmingham, and he's also the chair of the British Standards Institution's Forensic Science Committee. He's an active member of the International Organization for Standardization's Forensic Science Committee, and his past appointments include director of the Forensic Speech Science Laboratory at the University of New South Wales, scientific counsel to the Department of Legal Affairs at Interpol, and Simons Foundation visiting fellow at the Isaac Newton Institute for Mathematical Sciences. He's been involved in casework in Australia, Canada, Denmark, Northern Ireland, Sweden, and the United States. He's the author of many publications, over 50, and in forensic science, including being the lead author on the recently published Consensus on Validation of Forensic Voice Comparison, which we are going to be discussing today. And he's involved in different types of research and projects on inference or using inference and statistics applied to forensic voice comparison, fired cartridge case comparison, and also cell site analysis. And on that note, let me bring him in here. Hey, Jeff, how you doing today?
Hi.
Hey, great. Thanks for being here. So
Thanks.
We're going to start at the beginning here. I found it interesting. You actually, when I was looking sort of into your stuff there, you actually science and engineering, you started there and then you kind of migrated over a little bit. So I started in engineering as well. So my background was in aerospace, and then I kind of made what I felt was a career change anyway in this particular field. But were you always a technical person growing up, or was it always an area of interest?
Yeah, I think I was a very technical person. I think I had my first computer when I was 8 years old, which was the cutting edge back in those days.
Was that the VIC-20? What was that?
I had a TRS-80.
Oh man, yeah, that's even before.
Had 2K of memory.
Yeah. Right. Oh, awesome.
So,
and then what did you study in engineering?
I started off studying physics, right? But I was I had this strange interest at the time. I was interested in language as well as in science, and so it took me. I ended up having a very roundabout route to ending up where I am today.
Okay. And what was your main area of focus when you were doing your PhD? What specifically were you studying?
So that I was looking at speech perception by humans. I was particularly looking at second language speech perception, second language speech learning. There was a problem. So English has this contrast between E and I, those sounds like sheep and ship. And speakers of languages like Japanese or Spanish have difficulty learning those sounds because it's a contrast that doesn't occur in their first language. There's another couple of words that people, the thing that you put on a bed contrasts with something else, so people will they have problems with that. So that's, but what I was doing was statistical modeling of both speech production data and also perception, where we were synthesizing little steps between E and A. So in the acoustics, with just tiny little steps between E and A. And as you move along those steps, if a language English speaker suddenly goes, it was E, 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 and then they'll suddenly go, it's A. Whereas you get a more gradual pattern for somebody whose first language doesn't have that. So
So was that to help people with language, to help speak, or to help understand how the brain sort of?
yeah, I mean
Yeah.
the application, the potential application was in second language speech learning to trying to help people that were learning a new language. I had spent a few years. I used to live in Japan, and I taught English, and I was teaching pronunciation. I wanted to find out if that was working, and then ended up coming back doing a master's degree and a PhD. But it was very, in that sense, I was looking at language, but from a very technical perspective, where I was doing acoustics and statistical modeling of the results.
Right, right. And so that's where you first started getting into the statistical part of things?
Yeah, I think so. That was, I'd started a little earlier when I was working on my master's degree as to trying to find statistical tools to help me solve the problems I wanted to solve. And then my PhD I did at University of Alberta, because my supervisor that I went to work with my supervisor there, Terry Neary, who was one of the leaders in applying statistical models to understand human speech perception. So that's why I specifically went to University of Alberta.
I see. Okay.
And yeah, and then then I did a postdoc at Boston University.
Oh, okay.
And while I was there, I saw a job advertised which looked like somebody had looked at my CV, written a job for me, but instead of the question being human speech perception, where if you think about it, different people sound different, but we can still understand them. So the differences between people are noise that doesn't matter when our task is to understand what people are saying.
Mm-hmm.
And this job used all exactly the same skill sets I'd already developed in my PhD work, except the research question was the opposite. It was the differences between speakers that were of interest.
I see.
And so that was my first job in working in forensic voice comparison, which is what got me into forensic science.
Okay. Well, I'll tell you what. Why don't we? I mean, a lot of what you're doing with the forensic data and the statistics is applicable to many other areas, right? So,
Yeah.
but let's talk about the voice comparison very briefly, and then I want to move into some of the other areas that your work is applicable to. When it comes to voice comparison, how do people typically approach something like that? Like, what was the traditional way that people, you know, uh, analyzed a voice?
So I'd say it can be broken down into 4 different approaches. One approach is simply listening, right? And that's called the auditory approach.
Mm-hmm.
And people will listen and they'll try. I can hear some differences between the recordings. In my terms, I would say, what would be an interest? Am I more likely to hear those differences if they were produced by the same speaker or if they were produced by different speakers? But that's essentially the first approach would simply be by listening. There was another approach which was called the spectrographic approach, which was taking parts of the recording and turning the acoustic signal into a picture. But then the examiner would look at the picture and make a subjective judgment based on looking at the picture. Another approach would be what I would call acoustic phonetic, which involves making acoustic measurements of the audio recordings. And then those measurements could either be put into a statistical model, or what is actually very common is people would just then take the numbers, maybe make a plot of the numbers, and then again subjective judgment. And that was a tradition that came out of acoustic phonetics. It's making the same sorts of measurements as people make in acoustic phonetics, which were originally developed for doing things like what I was doing with my PhD, trying to understand what humans are doing. And then the final approach would be what's called an automatic approach, which comes out of signal processing, machine learning developments. And this would be the same approach that has gotten us things like maybe when you call your bank and it might ask you to say a phrase, and then it's a security system and will let you into your bank or not.
Mm-hmm.
So those developments were, but those systems were developed to be entirely automatic. Once you've set it up, you just set it going, and it doesn't require any additional human input.
Okay. So what are some of the, like in many other areas in forensics, right? There's always like a case or whatever that's, sort of the one that stands out. That's the example of, something went wrong or something like that. Are there any cases like that in forensic voice comparison, or are there any? Is there a good record with forensic voice comparison? How does it stand?
So, I mean, there was one of the approaches I talked. I mean, although I've said there's 4 different approaches, often a mixture would be used. So there was the spectrographic or the auditory spectrographic approach. This was developed in late 50s, early 60s, and by the late 60s, early 70s, it was very popular in the US. But it was a procedure which was based on subjective judgment.
Mm-hmm.
So it had technology to turn the acoustic signal into a picture, but then it was a human looking at the picture. And so this was very controversial as to whether it worked or not.
Right.
And the problems with testing whether something works or not is does it work under forensically realistic conditions? And so in fact there was a report that was I think the first version was issued in 1968. I think the published version might have been 1970 if I'm getting my dates right. Bolt was the first author, which was highly critical of this approach. And they were calling for the need to have the system validated. So the fact that it is a subjective judgment per se is not bad. But what they were asking for was for there to be a validation of the performance. So you would take the human examiner who's making the subjective judgments, and you would require them to do a whole bunch of trials where in some trials they're given a pair of recordings that do come from the same speaker. And in some trials, they're giving a pair of recordings that come from different speakers. And they give those under conditions that reflect the casework conditions. So the length of the recording, background noise, reverberation, transmission through telephone systems, for example, matching those conditions to see how well that human, in this instance, would do under those conditions. Giving them a whole bunch of same origin trials, a whole bunch of different origin trials, for which they must not know what the correct answer is.
Right.
But then the tester does, and then the tester can compare their answers with what is the truth. And so the complaints were that really there was a lack of that being done under forensically realistic conditions.
Mm-hmm. It was interesting. I was just thinking that the other day I was driving to work, and there were 2 radio announcers on. They were both female. They had almost an identical voice. And they, normally one may be higher pitched or lower, and their tone, their pronunciation was, and I could tell them apart, but they were very, very similar. And you've been talking about subjectivity, with you've mentioned that word several times, which seems to be a problem in every discipline. But do we have a good idea or handle on sort of the range of voices and the range of tone and that sort of thing, how people speak, people's voices?
I mean, one thing I can say about that, how people do this subjectively based on the existing literature looking at that is, I think one of the key things to take home from that is, in fact, people are worse at this than they think they are.
Mm-hmm.
right? So people's self-estimation of how good they are at recognizing voices, both in general, but also in instances when they are actually doing this task. They're overconfident when they're actually doing the task. You're asking, how confident are you in your decision? They're overconfident in that. And also then they're overly confident about how good other people are at the task.
I see.
Which has this very important implication for forensic purposes, where if it's for example if it's a judge just listening, or if it's a jury listening, or if it's there are instances where, say, a police officer's asked, oh, you heard the voice on the recording and you heard the suspect, and the police officer will come and give their opinion. But all of this being based on perception, and there's various factors that may influence whether somebody's better or worse at this, the conditions of the recordings, etc. But I think the key thing to take home is, in fact, people are overly optimistic about how good they are at it and how good other people are.
Right, yeah.
So I don't know about the whole range, if there's any sensible way to categorize that.
Mm-hmm.
But from perception, I think that's the important message.
Yeah, that's interesting. So when we come to more objective methods of analysis, are you still combining them with other formats, or is this like a hands-off automated thing? You run the audio through the let's call it the black box for now. It does its thing. There are different types of analysis, and it's always a comparison, right? Like, I mean, you have one, and it's comparing it to one or more sources of audio.
Right.
But what is it? What can you tell us about what it's actually looking for in the audio?
So the approaches I'm using are what I would call human supervised automatic. So it's this automatic approach which has been developed from signal processing and machine learning approaches. And there's been lots of work done in that over approximately the last 2 decades, which has been focusing on also, as I was saying, you can have poor quality recordings. You can have background noise transmission through a mobile telephone, maybe a police interview in a small room with hard walls,
Mm-hmm.
lots of reverberation. And so you can get poor or a very short recording. And you can get poor quality recordings, but also mismatches between the known origin recording and the questioned origin recording. So lots of work has been done in the statistical modeling to deal with these mismatches. So this results in the automatic system having by far the best performance of any of the approaches that I've discussed before. So that's the approach that I'm using. I'd said it's human supervised, and the human supervision is in selecting appropriate data to put into the system. Right, so you don't put garbage in and get garbage out. Mm-hmm. But there's expertise required there. I mean, there's some selecting appropriate statistical models, etc. But there's expertise in putting appropriate data in so that we get appropriate answers out.
Mm-hmm. Okay, interesting. And what about things that may be unique to, I won't say completely unique to a person, but for example, could sort of limit the number of people that maybe speak a certain way, or somebody that's from another country that English may not be their first language, or they say something in a certain way. Certainly, it may not be unique mm-hmm. to them, but if you're referring to a pool of people, mm-hmm. it may help to minimize, where that person came from, or might help right. to isolate a group of people. So how does that work? Because your pool, like when you have a couple of sources, if you're only dealing with 2 or 3 pieces of audio, how do you draw larger inferences from such a small pool of data?
So, we're looking at 2 things. We're trying to answer a question that has 2 parts. And the first part of the question would be, what's the probability of getting the acoustic properties on these 2 recordings if they came from the same speaker? So it's a question about how similar the acoustic properties on those two recordings are.
Mm-hmm.
And the second part of the question is, what's the probability of getting the acoustic properties on these two recordings if they came not from the same speaker, but from two speakers selected at random from the relevant population? So that's a question about how typical are these properties with respect to some population.
Mm-hmm.
And defining the relevant population is important. So, and the similarity divided by the typicality is what we call a likelihood ratio.
Right.
It's the same framework as is used for DNA, for people that are familiar with DNA. And so this is a framework which has been for a couple of decades. This has been, it's been increasingly used in forensic voice comparison. The relevant population, as I said, matters. So, you know, a common thing for us to do would be to say, we look at the question speaker recording, and usually, not always, but usually it's obvious whether it's a male or a female. I have had cases where that wasn't necessarily obvious, but
Mm-hmm.
usually it's obvious whether it's a male or a female on the question speaker recording. It's obvious what language they're speaking. And at least broadly speaking, we know what accents, we can tell what accent they're speaking. So, you know, do they have a Canadian accent or an Australian accent? You know, certainly at that level, it's fairly easy. And so usually we would be using these properties to say, what's the probability of getting these two recordings if they came from the same speaker versus if they came from two speakers who are a particular sex, speaking a particular language with a particular accent.
Okay.
And so, so part of that is answered by it's what, you know, that sets up what question we're answering. And obviously, if it's obvious that it's a male speaking with a Canadian English accent, then there's no point in including in our population female speakers of Chinese. Right? It wouldn't make sense. So, but we're defining what the question is. But maybe I should mention it for people may not have a very good concept of what's typical. So we're using statistical models. We're using data. So we need our question speaker recording, our non-speaker recording, but we also need a sample. Once we've decided what the relevant population is, we need a sample of a large number of speakers from the relevant population. And we need at least two recordings of each speaker. One would be under recording conditions that are similar to those of the question speaker recording. And one would be under recording conditions similar to those of the non-speaker recording. So, for example, if it was a mobile telephone intercept versus a police interview, the recording conditions are different. The speaking styles may be different as well. So we'd want, from our sample of our population, we need speakers from the relevant population, but also we need at least two recordings, one under each of those conditions. That allows us to do the calculations to be able to calculate. We can calculate the similarity and the typicality. We would take those data and we would say split them in two. Half we would use for training the statistical models, and then the other half we would then use for testing and validating to see how well the system actually performs under those conditions.
What kind of numbers are we talking about when you're talking about you're getting a sample size? I mean,
so the basic statistical models, if we're doing an automatic system, so state of the art is what's called an X vector system. The beginning of the X vector system is using a deep neural network. Then we have a back end of that, which is then calculating the actual likelihood ratio. That stage for the deep neural network is using thousands of speakers, hundreds of thousands of hours of audio, but trying to get the way these things are trained, us trying to use as large and diverse a set of speakers as possible. And it's being one of the important things for training these is to have a very large number of speakers, but then a lot of recordings for each speaker under lots of different conditions.
Mm-hmm.
Right. Sometimes they can do this by cheating. You can get one recording and add noise to it and create So you can create, it's the same speaker, but under different conditions. So then what the system is learning is with lots of speakers and then lots of recordings of each speaker under different conditions. Then the system is learning to pay attention to the differences between speakers and to ignore the differences between different recording conditions when it's the same speaker.
But are these volunteers that are coming into a lab, or is this stuff that's getting scraped off the internet and you know what I mean?
So this is, this is a mixture of data that were specifically collected for research purposes and stuff that's scraped off the
I
internet.
see.
So the example of something scraped off the internet would be there's a database called Vox Celeb, where they went and it's celebrities which they got off YouTube. And but it's doing a lot of signal processing. That system is actually looking at people speaking as well as the images as well as the audio, and scraping stuff out off YouTube of celebrities. But a lot of databases have been collected over the years. Most of this not specifically for forensic purposes, but for other maybe more lucrative applications. And so these are data sets that exist that get used to train this deep neural network system. Our challenge in forensic science is then what I'm calling the back-end models, which are, so this, if you think about this deep neural network system, it's giving you an X vector, and the X vector is just a fixed length vector, one fixed length vector for each audio recording. And then that's the input to a subsequent set of models, which actually calculates likelihood ratios. So for those models, we need recordings that are of speakers sampled from the relevant population and that reflect the recording conditions in the case.
I see.
And so this is our challenge. This is the thing that makes it very difficult to do casework. It's the obstacle is a lot of the time we don't have relevant data. And if we don't have relevant data, then it's very difficult to proceed because we can't calculate the likelihood ratios and we can't validate the system. Yeah.
Sorry, does your lab work on, like, is there a hardware system and then the processing or the algorithms and stuff? Are you working on both of those, or is it pretty much just nowadays it's just the statistical component or the theoretical component?
Yeah, it's mostly software.
It's mostly software.
Yeah, so it's coding stuff up in software. Yes, I've worked in data. We work in data collection as well. But the hardware for data collection is microphones, computers, etc. We're in the middle of developing a new protocol to try and help us do the data collection more easily. We're trying to develop some software where we're trying to automate things that in the past have been done manually by humans. And it would be, for example, a mobile telephone app that would suggest to the volunteers, hey, why don't you make one of these recordings, call your partner, have a conversation with them, and then it would then be directly uploading that recording to our server. So we've got, when I worked in Australia, we did a database of 500 plus Australian English speakers.
Okay.
And now we're trying to replicate some of that work, but trying to do it more efficiently by using technology. And that database is useful for me. I'm working on an Australian case right now.
I see.
So using that database that I collected when I was working in Australia. I did a case in Canada a couple of years ago, actually not too far from you. And the hearing was the court hearings were in Newmarket.
Yeah.
And that in that instance, it was the prosecution that asked for the work to be done, and the police were very interested in having it done. And we got recordings of 100 police officers making calls to the call center, five calls each of more than 100 police officers in less than 2 weeks. So that's, that exists as a solution, but a lot of the time, neither of those solutions exist, and so that's the impediment to doing
I
casework.
see. Okay. The paper that you recently published, and I'm just going to bring it up here because it's this one here: Consensus on Validation of Forensic Voice Comparison. You have a whole number of people here that are doing sort of in that family of work, and even though you've chosen forensic voice comparison, I mean, so many areas in forensic science are trying to get to a position where they can use statistics and likelihood ratios, regardless if it's footprint, blood stain, or whatever it is. We'd all like to move this way, and it would seem that the areas which are less binary, it's not like a very concrete thing, are probably easier to work with. So what can you tell us about this particular paper and how it can be applied to other areas?
Sure. So this is this is a paper that we developed. We started in 2019. We had a meeting in September 2019. I will say thank you to the Netherlands Forensic Institute. They hosted it. And what we did is we got together people that had experience in validating forensic voice comparison systems, but also experience in validating forensic science more broadly. We included lawyers or legal scholars that could contribute. And our scope that we narrowed it down to the scope of forensic voice comparison systems that output likelihood ratios, and in practically automated systems. And the question we were trying to address is there's already been quite a lot of work done on validating forensic voice comparison systems, but the question that we hadn't really been addressed is how do you know when it's good enough to take to court? Mm-hmm. And that could be a question that's being addressed by the practitioner or the laboratory deciding if they're going to submit their report, by a lawyer deciding if they're going to use it for a plea deal, or if a prosecutor is going to use it for prosecution, or it could be if a judge is going to decide whether it's admissible. How do you know when it's good enough to be used? And although we narrowed the scope down that way, and we narrowed it to forensic voice comparison, as you were mentioning, if you look at this paper and you change a few words, you could apply it to lots of other branches of forensic science. Of course, with the proviso that it's systems that are outputting likelihood ratios. Mm-hmm. Our conclusions is one of our key conclusions is, well, your system has to be well calibrated. And it has to provide useful information. So the threshold we came down with was, is it providing useful information? Was ultimately our decision on the threshold. And essentially, there is a metric which is the log likelihood ratio cost. And our conclusion was, as long as the log likelihood ratio cost is less than 1, then the system is providing some useful information. The lower that value, the more useful it is. So that was a threshold conclusion. But that paper talks about multiple issues around how to do validation of systems that output likelihood ratios. By narrowing the scope to forensic voice comparison, we could produce what I think is a more progressive document, because we have a group of people working in forensic voice comparison who, for a number of years, have already been working on trying to solve the problems of how do you measure how well calibrated a likelihood ratio system is, and how do you actually, what are the protocols that you should use? Things like, well, you need to do it under forensically realistic conditions.
Right.
That reflect the conditions of the actual case.
And it would seem that you need a good population, or you need a good size somehow. So is that often a challenge to get, or is that pretty simple?
Yeah, so well, that is the challenge.
Mm,
So that's the challenge both for being able to do a case, to be able to calculate the likelihood ratios that are answering the relevant question. So I mentioned the system has to be well calibrated. In order to do that calibration, you need data that reflect the relevant population and the conditions, the recording conditions of the case. Or if you would say, if it was fingerprints, for example, and you've got a nice rolled fingerprint on one side, but you've got a partial distorted print on the other side, those would be some conditions.
right, right.
And you've got to have, so you've got to have those data to, if you have it under some other set of conditions, you're answering a different question. You can throw these data into your statistical models, but they're answering the question with respect to the data you actually put in, and that would lead to a system that would be miscalibrated with respect to the question you actually wanted to answer. So without data that match the question you want to answer and the relevant population and the relevant conditions, you can't calculate well-calibrated likelihood ratios. And without those data also, you can't validate under those conditions, right? So if you validate under some other set of conditions, that doesn't necessarily tell you anything about how well it's going to work when you apply it in this case.
Okay.
So this gets us back to those are the practical challenges. And so we still, I would say our challenge is to have development resources to develop databases that reflect forensic conditions.
Yeah, that's fair
so
enough.
that we can then proceed.
Yeah. There's another paper here. It was a comment on the PCAST report, skip the match, non-match. And as I was going through this, there was a part in there, and I'm hoping you can just sort of clarify this for me. But there's a sentence that says, almost always measurements made in feature comparison methods will naturally result in continuously valued data within source variability. And I just want you, can you help explain that to me, what you mean by that? And what are the issues with this match, non-match?
So if you think about traditional DNA, these are discrete data. So with a few minor exceptions at a molecular level, if I take a DNA sample from you today and I take one from you tomorrow and 10 years from now, and I look at the particular loci at a molecular level, your DNA should not have changed. It will be exactly the same. But also what they're counting short tandem repeats, which are then discrete numbers at the loci. So you have a particular count for an allele, and it could be 19, or it could be 20, or it could be 21, but it can't be 19 and a half.
Mm-hmm.
Right? It has to just be one of these discrete values. And so they're discrete values, and also it doesn't change over time. So what that means, if I take 2 DNA samples from you, it doesn't matter how far apart I take them, as long as we're assuming the simple DNA cases in which we've got plenty of DNA, it's not mixed with other DNA, and we get the profiles and nothing went wrong in the process, we didn't get any contamination along the way, then those 2 profiles will match exactly. The numbers are discrete. It's either 19 or 20. If your allele was 19 and the profile came back 20, and assuming there was an error along the way, then it ain't you.
Right.
So then in that case, when you calculate the numerator for the likelihood ratio, it's either a match or it's not a match. So if it's a match, the numerator, the probability in the numerator is 1. If it's not a match, the probability of the numerator is 0. And therefore the likelihood ratio is 0.
Mm-hmm.
And then, so now what are we left with? We need to worry about the denominator. If the numerator is 1, what we need to worry about is the denominator. So that's what's the probability of getting this exact profile from somebody selected at random from the relevant population. And we get back, so usually in DNA it would be by geographical region, it may be by country, and also sometimes by ethnic appearance. And so they will select the relevant populations that way. But then the numerator is 1, it's an exact match. And the denominator is just the random match probability. So what's the probability of getting that profile from somebody picked at random from that population?
Okay.
So those are match, non-match works in that context in the simple DNA models when the data are discrete and invariant. But if we talk about speech, for example, the things that we measure about speech, if I measure the fundamental frequency, so that's, if you like, the pitch of the voice. So I can have a deep voice or I can have a high pitched voice. But I vary from occasion to occasion. My intonation, my pitch is going up and down within the recording, within this recording. We could average it over the entire recording. But if you make another recording of me at a different point in time, you're not going to get exactly the same number.
Right. And
it could be, we would measure it in hertz, but it could be 100 hertz, it could be 101 hertz, it could be 102 hertz, but it could be 99.999 hertz. It could be 100.0001. It could be any number. It's continuous. So you can no longer use the numerator as either 0 or 1. And you need to calculate a probability for the numerator.
Okay.
And you need to calculate a probability for the denominator. And so the PCAST proposal, we can actually look at the PCAST proposal and say, actually, this is consistent with the likelihood ratio framework. But it's got a threshold on it. So what it's saying is you're taking something that may be continuously valued. So fundamental frequency, there's other things that we could measure about voice. Let's say we could measure something about the spectrum of fibers. We could look at the colors of the fibers and we get a spectrum, and that's going to have some sort of continuous value to it. We could look at refractive index of glass. That's got a continuous value, and you take it from a different part of the window, it's not going to be exactly the same number. So the PCAST idea is to put a threshold on that, and then if it's within the threshold, if the difference from your known and questioned are within a particular threshold, you say it's a match. And then you're looking for what's the probability of getting something in your relevant population that was in that threshold range, right? Or sometimes they were talking about it in the PCAST report as the examiner declares a match using whatever criteria they've declared. And then what would be the probability they would declare a match? So if it, in fact, were not the same source. Right, so we'd have to do tests of the examiner, which again, this is now maybe the examiner doing it subjectively. We'd have to test the examiner. We'd have to give them a whole bunch when it is a match, when it is the same source, genuinely the same source, a whole bunch when it's generally a different source. And then we'd have to see what's the probability they would say same source if it is same source. What's the probability they would say same source if it's actually different source. That would actually give us a likelihood ratio. However, it's on this threshold. And this threshold actually throws away lots of useful information, right? So it ends up, you can only have 2 likelihood ratio values. You can have the likelihood ratio value for when a match is declared. And you think about it, if you're just beyond the threshold, if you're on the other side of the threshold, then you get treated very differently. If you're on the match side of the threshold, then you get this single likelihood ratio. If you're on the other side, then you say not a match, right? Then we could say, well, what's the probability of declaring not a match if it really was not from the same source versus if it was from the same source? Then you get that other likelihood. But in fact, the difference, if I go back to 100 hertz, if it's 99.9 hertz and 100.1 hertz, they would get treated very differently. So there's a problem there with the threshold. Yeah. The other would be, let's say my threshold, I could be just beyond the threshold or it could be very far beyond the threshold. They get treated the same, right? Whereas in reality, maybe just beyond the threshold and far beyond the threshold, that far beyond the threshold, maybe that's should be a lot stronger strength of evidence. and the two that we talk about a cliff edge effect, the two that are actually very similar that get treated very differently. So, so what that proposal, and again, I think there was 18 authors on that one.
Yeah.
That's saying, and in fact, this is not new. We see this pattern happening again and again. It happened for DNA, for example. People had proposed models like this that are, and then we've developed and come along and we've developed models that are based on continuous values.
Okay.
And so this better exploits the information. We get better results when we measure the performance. We get better performance. And the match non-match is ignoring lots of useful information, and you get a threshold effect as well. So, so that was a paper we actually published that, or that paper. The original version was published within, I believe, approximately 1 month of PCAST being reported. So I think it was the first article published in a referee journal commenting on PCAST.
Which would have been around 2016, right? 2016
yeah, it was. Yeah, it was. In fact, at the time, there was. I was at the Newton Institute. There was a conference going on at the Newton Institute, and so there was a lot of people around to help put this together. But it's something that we've known for a while, and it's kind of PCAST was reinventing the wheel in that sense. And what we wrote in there said we're very supportive of the core message of PCAST, which is you need to do validation.
Okay.
But we were trying to be supportive and say, but we think there's a better way than the particular solution that they came up with there.
Okay. What about, you mentioned that, or I read that you were doing some work, or maybe beginning some work on the fired cartridge cases and looking at cartridge case comparisons. And that's something that potentially could change over time, certainly as the gun wears or that sort of thing. What kind of plans do you have for that type of research? You're going to take the same type of model and then apply it to cartridge cases?
Yes. So our plans. I actually have a postdoc, Nabanita Basu, who's working on the statistical modeling right now. We're working with Rachel Bolton King, who's got expertise in firearms. I'm no expert in firearms. So Rachel is helping get the data. And if anybody has, so I'm going to put in the ad right here. So we're doing this on a particular class of gun that fires 9mm Luger. And what we're trying to collect is fired cartridge cases fired from 1,000 guns of this class. I get full screen for the ad, apparently. And we want 10 fires from each gun. And so this is the database we're trying to collect. If you can help us with that, please get in touch. And then what we're doing is, so Rachel has the loan of an Evo Finder system, which is a scanning system that's commonly used in forensic labs. So I plugged Evo Finder. Thank you to them. Then that maybe they'll let us keep it for longer. It's on loan.
You never know.
So we're using it because it's commonly used in forensic labs. So what we're developing has potential for real world application. So Rachel is then going to be scanning the 10 cartridge cases from each of 1,000 guns, which gives us our database, which now we have a sufficient scale both between source variability with a large number of guns and within source variability with a relatively large number of fires from each gun.
Right.
And that's essential. A lot of the existing databases, they're maybe 100 guns, but 3 fires from each gun, or a lot of fires from a smaller number of guns. We're going to this larger scale, for both number of guns and number of fires. And that will allow us to start building these statistical models. And in fact, the statistical models we use for forensic voice comparison, because they're based on continuously valued models, and multi-dimensional data. It's complex data. It's continuously valued. It varies from occasion to occasion. This is more similar to the kind of data we're going to get off the scans of the cartridge cases. So it's 3D scans, and then we put those into signal processing algorithms, and then we're going to put them into the same sort of statistical models that we're using for forensic voice comparison to be able to calculate likelihood ratios. And one of the other advantages of these models that we're using in forensic voice comparison, people have been trying to do this sort of thing in cartridge cases, but also in other branches of forensic science, and they're taking the two things and then they're measuring the distance between them somehow. So for cartridge cases, it could literally be you take one scan, you take the other scan, and you look at the correlation. You line them up, and then you look at the correlation, and it's like a distance between them, or a degree of similarity between them. Unfortunately, if you're measuring degree of similarity and then trying to calculate a likelihood ratio, it doesn't work because you've not taken account of typicality. Mm-hmm. So for people that know about probability density curves, if I have a probability density curve like this, and I've got these two things, and they're that far apart, but they're in the middle of the probability density, then if I were to pick two items at random from that population, there's quite a high probability I would pick two that are very typical in the middle of the distribution, and therefore they would be similar to each other. Whereas if I put these on the edge of the distribution, off the screen, if these are very rare, the probability of picking these at random probability of picking one at random is small if it's on the tail of the distribution. Probability of picking two at random on the tail of the same distribution is much smaller. But a model that only is based on the similarity or the distance between the two objects will ignore that typicality aspect.
I see.
So the models that we're already using in forensic voice comparison don't do that. They make I talked about X vector. There's an older generation I vector, but they're making a measurement. We get one number. We'll get one number for one cartridge casing, another number for the other cartridge casing. And then we can put those two numbers into statistical models, which are not similarity based, and we'll calculate likelihood ratios.
Do you find that there's any resistance? I mean, is anyone resistant at all to adopting some of these new methods, or is there some contradicting or combating methods for this type of method going forward?
I would say that we are in the middle of a paradigm shift. Sachs and Kohler published a paper in 2005, which was the coming paradigm shift in forensic science, if I remember the title correctly. It was published in Science. I think, actually they said something in that paper, we don't really mean a Kuhnian paradigm shift. I think it really is a Kuhnian paradigm shift. In the sense, there's lots of parallels. The nature of a paradigm shift is there is resistance to a paradigm shift, sometimes for very rational reasons, but this is what happens. I look back I've been working since 2007 in forensic science, and I started off working in forensic voice comparison, and I see progress in that time period where there was a lot of resistance to using the likelihood ratio framework. And within the last 5 years, people seem to have been much more accepting of the use of the likelihood ratio framework. And there's still resistance to the idea of having to collect data, that you need to collect data for calculating the likelihood ratios and for validating your systems. I see resistance to the idea that you have to validate. Mm-hmm. I mean, certainly you look at that, PCAS comes out, says you need to validate, and you immediately get a whole bunch of responses. No, we don't need to do that.
All right.
So look, there are lots of flaws with the PCAS report. However, it was written by real scientists, not just forensic scientists, but people who understand the norms of modern science, and the need to validate is there.
Interesting.
So I do see so I see progress in forensic voice comparison. I think other branches of forensic science, there is resistance.
Okay.
Um, one,
There's actually,
I was going to say one of the solutions we need, of course, one of the rational reasons for resistance is how do we do it? And so what kind of my research program is about trying to provide data and trying to provide statistical models and tools to allow people to do it. So
right.
it's no good. It's no good coming in and say, "Hey, you've been doing it wrong. Stop doing it wrong." You have to try to help and be constructive and provide tools.
Yeah,
So
that
that's
that usually doesn't go over well. So,
yeah, yeah,
yeah. Hey, we're getting on in time, but if you
right.
wouldn't mind taking a question, actually, there's somebody here, Mason Lin. He says there were many, I guess, forensic science studies over the last 2 decades in China that simply used a one-way ANOVA test and SPSS to calculate the data. Is that an alternative for the likelihood ratio framework? And then he goes on to say, or is the likelihood ratio framework a better one?
Well, I'm going to say the likelihood ratio framework is a better one.
Of course.
No, these things are philosophically at odds with each other. That would be that might null. So I mean, the ANOVA is you'll be doing there are some things in ANOVA that the F value in ANOVA is likelihood ratio like. However, probably you're doing an ANOVA, you're getting a p-value out of it. You're doing null hypothesis significance testing, and certainly the vast majority of statisticians, especially in recent years, there was a when did it come out? 2007, or was it earlier? There was a statement made by the American Statistical Association saying stop using null hypothesis significance testing. There's been lots of papers written about that. So these are different paradigms. I have a colleague in China, Professor Zuiling Zhang, who has worked with me for a number of years, trying to do like calculating likelihood ratios and validating, etc., in forensic voice comparison. And we've done some research on Chinese, but if it's an automatic system, it's Chinese, it's English, it's
Right,
whatever,
right.
it doesn't really matter.
What? So let me ask you. Last question. What is the next big thing for you? What is the next area of focus? Next big thing or next area that maybe you'd like to move into?
So I want to continue my paradigm, my program of trying to adopt this paradigm. So we're trying to do logically correct evaluation of evidence, i.e. the likelihood ratio framework, transparent approaches that are replicable, which tends to push us towards approaches that are based on relevant data, quantitative measurements, and statistical models, and also resistance to cognitive bias, for which again, relevant data, quantitative measurements, and statistical models are a solution. And that I want to try, and so I started doing this in forensic voice comparison. I write papers that are about validation, about calibration, about issues that are generally applicable. We are currently working on a firearms project on the cartridge cases. You mentioned cell site analysis. We're just beginning that. Matt Tart is somebody who I'm working with, who's a practitioner who wants to work with us on this. And that's one of the secrets there is finding collaborators who researchers and practitioners in particular fields who want to do this. There's no point in trying to convince somebody that they need to do it.
Mm-hmm.
We need to find people who really want to do it, to be collaborators. And I want to keep doing this into different branches of forensic science. I think the next step is to seriously get work started with the work on the cell site analysis.
Excellent.
And I've been talking to people about working on fingerprints. And actually, both cell site analysis and perhaps even more so, fingerprints would have a lot of impact. Another area we're talking with potential collaborators about is gate analysis, which
Mm-hmm.
is that
Mm-hmm.
kind of gate, not the open and closed gate. the fingerprints is definitely a challenge. It could have potentially the greatest impact, but culturally, when you were talking
Yeah.
about resistance before, that's an area where culturally there may be a lot of resistance. But I look back, a lot of existing work has been done by and papers published by academics, and it just stays as an academic publication.
Mm-hmm.
And so that's the other challenge, is to be working with practitioners who want to do this, to actually have a real world impact. And so
Yeah.
all of my work, we're trying to do end user needs assessments and work with practitioners who are then going to be the people who would actually be able to adopt this in the long term.
Well, I think that's it. It's part of the challenges is always the people
Yeah.
issue, right? Not always the technical issue, but that's why you're here. You're here to
Right.
educate people, and I think that's part of it. Hey, listen, I want to say thanks so much for your time. It's something that is sometimes difficult to digest, like depending on the type of area that you're working in, and I think we all realize we all want to push in this direction, and so obviously some of the work that you're doing here. Uh, we need to follow relatively closely here because of the implications that it has in other areas. So thank you again for being here, and hang back. I'm going to come back and just
All
speak to
right.
you.
Well, thank you very much for inviting me and giving me the opportunity to talk about this topic.
All right. Thank you, Jeff. All right, folks. Well, that does it for this episode of Forensics Talks. And next week, we are going to be speaking to Dr. Teresa Stotesbury. She's a forensic chemist from Ontario Tech University, and she's going to talk to us about the kinds of information you can get out of bloodstains and bloodstain patterns. And she's doing some really interesting work with like deterioration of blood and that sort of thing. So, see you next Thursday, 2 p.m. Have a great day, everybody. Bye bye.